Hello, today I'm going to give you an introduction to complex numbers. Now these are a special type of number that were first introduced by mathematicians a very long time ago, I believe maybe in the 1500s, and the reason they came about is because mathematicians wanted a way to express the solutions to equations like quadratics that didn't appear to have real number solutions. So if you think back to your solving of quadratics, you'd have the formula, and there was a particular part of the formula that had to be equal to 0 or greater than 0 for you to be able to actually write the solution down. And that bit was the discriminant. So to give you a little reminder, that was b squared minus 4ac. So when this thing is negative, we would run into the problem of not being able to actually work out the solution to the equation. And we would say there are no real solutions. Mathematicians don't like not being able to solve things, so we needed to come up with a way of expressing the solution to this, even though they don't seem to be numbers that actually exist that work for it. And that's because we were trying to do the square root of a negative number. So let's start with an example so we can see how we actually deal with getting a solution that doesn't appear to be real. And where we would normally write a quadratic in the variable x, when we know that we're going to be working with complex numbers, we use z to represent our unknowns. So the quadratic that we're going to use as an example today is going to be z squared minus 8z plus 41 equals 0. So let's see what happens when we try and solve this. We're going to use the formula. So we've got a is 1, b is negative 8, and c is 41. So if we'll put that into minus b, so that's going to be 8 plus or minus the square root of b squared, 64, minus 4 times a times c, so that's just going to be 4 times 41, all over 2. So we can see that under the square root we're going to end up with a negative. So 4 times 41, that's 164. 64 minus 164 is negative 100. So before learning about complex numbers, this would be a point at which you would say there are no real solutions. However, if we have a way of expressing the square root of negative 1, then we can separate the square root of negative 1 out from the 100 and actually have a way of writing this answer down. And this is the first main new thing to learn here, and that is that the square root of negative 1 is now expressed as I. And we've chosen I because, or mathematicians chose I, because these are imaginary numbers. They are not real numbers that you can make any sense of in the real world. So this now means that our expression, our answer over here, becomes 8 plus or minus, now the square root of 100 we can do, that's 10, and then the square root of negative 1 just becomes an I. So when we see numbers that have an I in them, we know that they came about from doing the square root of a negative number. So this one here can be simplified. So 4 plus or minus 5i are the two solutions that we have to our quadratic. As we have always expected, we can get up to 2 solutions from our quadratics. Now we know we always can because we're able to use these complex numbers. Let's do another example. So let's have z plus 18, z squared, sorry, plus 18 equals 0. So this one we don't need the formula for, we can simply move the 18 over and square root. So obviously we're doing the square root of negative 18 here. So this time we know that the negatives can become an I, and then we just deal with the square root of 18. We're going to want to give our answer exactly, so we're not going to actually work out the square root of 18, but what we can do is simplify. So that's going to be 3 root 2. And then we just stick our I on the end to say that this came from doing the square root of negative 18. So that's how we express our solutions in a complex way. Let's just talk a little bit more in general about these complex numbers. So if you have, I don't know, some multiple of I like 3i or maybe minus 7i, you can even times I by pi, And that's a slight exception to the general rule of writing the number in front of I. When you have a pi involved, we normally put the I first. But all of these types of numbers where we just have some multiple of I, these are what we call imaginary, because they are entirely made up of imaginary numbers, these root negative ones. And then if we bring in a real number as well, so for example the 4 plus 5i that we just got as a solution, or maybe something like 7 plus 8i, or minus 3 plus the square root 2i, anything that has a real part and an imaginary part, these are what we call complex, because they have both real and imaginary. And you'll see that we write a general complex number representing z, and we normally write it something like a plus bi, where a and b are both real numbers. Then we're able to do things like take the real part of z, so that looks like writing re for real of z, and that would be a, so just real part is a, and then imaginary, we do a similar thing, so we put im for imaginary, and the imaginary part of z here would be b. Okay, so let's think about what happens when we start raising I to various powers. If we start multiplying I by itself or by itself 3 times, what kind of things happen? So let's see if there's a pattern to this. Let's start here. So I to the 1, that's just going to be I. What happens if we square I? Well, that's going to be taking the square root of negative 1 and squaring it. So actually squaring an imaginary number results in a real number, and then squaring I itself results in negative 1. What happens if we cube I? Well, we take the previous answer, I squared, and we're going to times that by another I. So that's going to be minus I. Okay, so timesing by I once gets us I squared, which is minus 1. Timesing by I again just gets us minus I. I to the 4. What happens this time? Take our previous answer. So I cubed times by another I. So what's going to happen this time? Well, I cubed was minus I, times by another I is going to give us minus I squared, but I squared itself is minus 1, so that's actually going to give us 1. And then if we go on from there, I to the 5 is going to be I times the previous, so I to the 6 is going to be I times the previous, which is I squared, which is minus 1, and we start following this pattern. So starting from a power of 1, we're going I minus 1 minus I 1. And then it'll keep going I minus 1 minus I 1. So because there's a pattern to this, we can actually work out, I guess, kind of random powers of I, like for example I to the 49 without too much trouble, because we just think, well, every multiple of 4 is going to be, every power that's a multiple of 4 is just going to be 1. So let's break this number down into the highest multiple of 4 we can possibly get, which is what, 48. So I to the 4 raised to the 12 gets us 48, and then we would just need to times by another I to bring it up to 49. So I to the 4 is just 1, to the 12 is just 1 times I, so I to the 49 is actually just I. So it's all about multiples of 4 when you're looking at the powers of I. And there's just one more thing we'll have a look at to do with complex numbers in this introduction video. We'll do a lot more in other videos, but maybe let's just consider what happens when we do things like expand brackets that contain some complex numbers. So let's consider the examples 7 minus 3i and 2 plus I. So we'll have a go at just doing expansion of double brackets here, see what kind of thing happens. So if we multiply this out, we're going to get 3 times 2 is 6, 3 times I is 3i, minus 7i times 2 is minus 14i, and then minus 7i times I, so minus 7i squared. Now as soon as you get an I squared appear in any of your calculations, you're going to immediately replace that with negative 1, because we know that that's what it actually equals. There's no point or like leaving it unfinished if we don't actually evaluate it. So we can put our i's together and we can put our real parts together. So we've got 6 and we've got minus 7i squared, which is now minus 7 times minus 1, which is actually plus 7. So we're going to add 7 onto 6 to get 13, and then 3 minus 14 is minus 11, so we get 13 minus 11i. So the expansion of the double brackets actually results in just another example of a complex number, because our powers of I simplify back down into ones, minus ones, or some multiple of I. So let's do a slightly more interesting example. Let's actually take a triple bracket, but we'll make it nice. And we'll just do 1 plus I, nicest numbers we could possibly have, and raise it to the 3, so we can use the binomial expansion on this. Okay, so let's use our Pascal's triangle coefficients. That's going to be 1, 3, 3, 1. So we've got 1 cubed at the front, and then we're going to have 3 lots of 1 squared, which is just 1 times I, then 3 lots of 1 to the 1 times I squared, and then finally I cubed, and then we can go through and evaluate these powers of I. So 1 plus 3i, that stays the same. This becomes negative 1, so that becomes minus 3, and then I cubed is minus I, so that we can just replace with minus I. Then we can collect together our real parts and our imaginary parts. So 1 minus 3 is minus 2, and 3i minus I is plus 2i. So what's really nice about these is that even if you do quite a large power expansion of these brackets, because we can replace these higher powers of I with much simpler terms, they end up simplifying really nicely. So we'll do one more example. We'll keep it 1 plus I, but let's raise it to the 4 and see what happens in that case. So this time it's 1, 4, 6, 4, 1 from the binomial expansion. So it's going to be 1 plus 4 lots of I. I mean, we have got 1 cubed in there as well, but that's just 1, so we don't actually see the powers of 1 when we're doing this. Then it's going to be 6i squared plus 4i cubed plus I to the 4. And evaluate our powers of I. So the first two terms stay the same. Then we get minus 6, replacing the I squared with minus 1, minus 4i, because I cubed becomes minus I, and then just plus 1, because that's what happens with I to the 4. And we get something quite nice happen here, because we've got a plus 4i and a minus 4i, so they're going to disappear. And we've got a 1 and a 1, that's 2, and a minus 6. So actually this time we get a purely real answer from raising our imaginary expression to the power of 4. So, you know, there might be something interesting going on here. Maybe you could have a little look yourselves at higher powers of 1 plus I, see if you can spot any patterns. And that's going to be it for the introduction. So we've got an idea of what a complex number is, what an imaginary number is, why it came about, and a little bit of how to manipulate them. There's going to be more videos on this topic, and the next one in particular is going to be about complex conjugates, and it's going to have a little look deeper into things like dividing by complex numbers and the relationship between the roots to quadratic equations in particular. So I hope you found it helpful, and if you did, please leave a like on the video. Subscribe to the channel if you want to see more like this, and I will see you in the next one. Bye.